We discussed why we call them spot speed and when should we do it, what are the uses, some definitions, the methods of data collection. Once we collect it, we have to develop it in the form of frequency distribution table. Then you can prepare these figures out of it. Then you can calculate some important statistics from it. They are divided in two types: central tendency and dispersion. Okay, and central tendency. What are the things included in central tendency? Anybody remembers? What are the things included in central tendency? What are the statistics included in central tendency? What things are included in the statistics of central tendency? Tell me. Yes, anyone? When we say statistics of central tendency, what are the things included in it? What is this? Mean. So my Arabic classes are still going on, huh? Median. Okay. Mode. And there was one more thing. What was that? No. Mean and average. We didn't calculate basically any average. We just use the mean. Okay, very well. The other thing was pace basically. Okay, pace, which is a 10 miles per hour range in the middle of the data, which has more observations than any other 10 mile per hour range. Okay, so these are the central tendency. And then for dispersion, we used standard deviation. We calculate them. Then we have percentage of vehicles in the pace. We have to do it from the graph. And we have the 15th and 95th percentile, which also comes from the graph. And that these values can be used for calculating standard deviation as well. Okay. Then we moved on to the next part of the analysis, which is about the data itself. And we said the data, any real world data, follows normal distribution if you have enough samples for it. So a normal distribution looks like this, a bell-shaped curve. Okay, and you can represent it or you can write it mathematically in this form: x follows normal distribution with mean of 40 and variance of 25. And if there is another normal distribution which is called as standard normal distribution, and standard normal distribution is that normal which has 0 mean and 1 variance. Okay, and obviously speed data cannot have this. Speed data cannot have mean of 0. So you can convert your speed data or any data into standard normal using this equation. Okay, where x is the value in the data, mu is the mean of the data, and sigma is the standard deviation of the data. Okay, so this equation converts any x value into is standard normal equivalent. Okay, another thing which is related to the data, uh, when you get the standard deviation of the data, it tells you how much variation is within the data itself. Okay, how much variation we have within the data itself. Now my data is not the only data which is available. Okay, so in the last example which we did, we had 368 values. That doesn't mean these are the only 368 drivers on this highway. There are thousands of drivers every day. So my data does not represent the full population. Okay, my data does not represent the full population. So when I calculate standard deviation, it gives me variation of the data itself, those 368 values. Okay, but can this data give me variation in the overall population? Okay, because I cannot say my my variation in my sample of 368 is 6 miles per hour. So the whole population has the same variation? No. Okay. So how can we use the sample standard deviation to calculate the variation of the entire population? Okay. That thing, that value which represents the variation of the entire population is termed with E, capital E, and we call it standard error. Okay, so standard deviation is for the sample, standard error is for the whole population. Okay, it is not possible for us to get all the values for the population. Okay, it is not possible. Even the devices cannot do that, because devices also need maintenance. They also have some error, they also sometimes do not work properly. Okay, so to have 100% population for the full lifetime is not possible. So we always have a sample. So how do we get the standard error from the sample, the variation of the population from the sample, using this equation which you see over here? So S is the standard deviation of the sample, and N is the number of values in the sample. The standard deviation of the sample and number of values in the sample. Okay, so I have a sample. The variation in the sample is standard deviation. I use that variation to calculate the variation of the whole population. Now, another thing which I have for the sample is mean. Okay, it's mean. Is this the mean for the entire population? The answer is no. This cannot be the mean of the entire population. Okay, so how? So mean means the central value, right? We call it the central tendency. So mean is a central value. So how much is the, or where is the center of the population then? If the mean of the sample is here, then where is the mean of the whole population? For that we use a theorem. You call it the Nazariya, right? So we use a theorem which is called as central limit theorem. Nadhiyatul Haddul Wast. Okay, somebody told me. Okay, so I believe it's not completely correct, but anyways. So there is a theorem for normal distribution. Remember, it is coming from the assumption that the speed data follows normal distribution. We already saw it here. The speed data has a bell-shaped curve which follows normal distribution. So when you establish this, the speed data follows normal distribution, then the next item can be this. Okay, then the next item can be, you can find out the center of the population using the sample, if we have normal distribution. Okay, not for any other case. It's only available for normal distribution. Okay, so this theorem is only available for normal distribution. So what the theorem says, 95% of the population is within mean plus minus 1.96 E, where E is what? Standard error. Remember, we already talked about it. Okay, so if you have the mean and you do 1.96 plus minus E, or plus minus 1.96 E, you will get the range for 95% of the center of the data. Okay, and if you do 3 times E, then you get 99.7% of the center of the data. Okay, so if this is my data, and okay, and this is my mean somewhere in the center. So if I do from the mean, I go 1.96 E on this side and 1.96 E on this side, then in this much you have 95% of the center of the data. Okay, and from the mean, if you go 3 times E here and 3 times E there, so plus here and minus here, you will get 99%. So this much is 99% of the center of the data. Okay, in the books they explain it in another way as well. They say where these ranges 1.96 E and 3 times E, they represent what? They represent if you took, for example, 100 samples. If you took 100 samples, 95% of those 100 samples will have a mean in this range, mean plus minus 1.96 E, and 99.7% of the samples, in that means what? Almost all the samples, right? 99.7% means almost all the samples. So almost all the samples will have a mean within mean plus 1.96 mean plus minus 3E. Okay, so either you consider 95% of the center of the whole data or 99.7% of the center of the data, or you say it is the mean for 95% of the samples or the mean for 99.7% of the samples. Both explanations are used, but the point is this theorem, this nathuriya, gives us the idea about the center of the data. So E gives us the idea about the variation in the data. Which data? Population data, okay, not the sample data, population data. And the theorem gives us an idea about the center of the data, okay. Now in the previous case, the example which we have done, okay, our mean was 48.0 miles per hour and our standard deviation was 6.1 miles per hour, okay, something around this. Maybe I made a mistake in some fractions, but doesn't matter. So if I want to calculate 95% of the center of the data, okay, first thing is I'll need the E value, okay. So E value is standard deviation 6.1 divided by square root of n, okay. My n was 368 values, okay. So how much is my E here? 6.06, okay. Go ahead, how much is my E? Okay, 0.315. Then my 95% center of the data is mean, which is 48.0 plus minus 1.96 into 0.315. So how much is that? How much is this range? Okay, one value, and the next, this is with plus, right? So with minus, how much? Okay, good enough. Okay, thank you. So if you took 100 samples, different times, 95% of those samples will have a mean within this range. Okay, this is what it means. Or if somehow you took the whole population, 95% of the population will be in this range, in the center. Okay, this is what it means. Okay. And then if you want 99.7%, you can just replace this 1.96 with 3. Okay, and everything else will remain the same. Okay, this is what we have done. Okay, so we did 95% and you can do 99.7% if you want. Okay. Yeah. Now, I said if this theorem only applies if you have normal distribution. For normal distribution, requirement is real world data and enough samples. Real world data, enough samples. Real world data, we know we have speed data, which is real world data. I cannot have speed data in a lab. It's real world data. Then the next thing is I should have enough samples. So how much is enough samples? Okay, how do I know that I have enough samples? What is the number to check? Okay, so for that For example, first of all, you have to think about, you are trying to cover how much of the central population. So I already gave you the central limit theorem gives you two ranges, one for 95%, the other one for 99.7%. Okay, there are other ranges as well. Theorem also has a range for 60% of the data, but obviously we don't want to go into that. Huh? You don't want 60%, right? You don't want what is that, D, right? You want more than that. So we are not looking for 60%. So 95 and 99.7% are the reasonable, or the ranges which we are looking for. Okay, so in that case, first of all you have to select with between one of them. So when I select, let's say 95%, so what is my equation here? From the mean I am willing to go 1.96 e plus and minus. Okay, so I'm looking for the mean actually. What is the most likely value? What is the most expected value? That is the mean. From this mean, when I choose 95%, I am accepting a difference of 1.96 e from the mean. I'm accepting it, right? So this becomes acceptable error. This whole thing, not only the e, the whole thing, 1.96 e, it becomes the acceptable error. The difference from the mean I am willing to accept. Okay, this is if you choose 95%. If you have chosen 99.7%, then 1.96, it will not be 1.96 e, it will be 3 times e. Okay, so this the difference becomes your acceptable error, and we are representing acceptable error with a small e. So there is a capital E which is the standard error, and there is small e which is the acceptable error. Okay, so you choose which one you are going for, which limit you are going for, 95% or 99.7%, and then you know how much is your acceptable e. Now in this equation, you can see in the small e equation, I have 1.96 e and capital E, 1.96 and capital E. Capital E was standard deviation upon root of n, standard deviation upon root of n. I'm looking for n, right? I'm looking for the sample size. Sample size is what? N. Okay, so I want the equation for n. So small e equals 1.96 s upon root of n. So I will take n on this side and this on this side. Okay, and I have to remove the root as well. So once I do this, I get these equations. Okay, so when you remove the root, everything becomes a square. 1.96 square is this thing. Okay, and if somebody went for 99.7% interval, then small e will be 3 times e, capital E, and capital E will be s upon root of n. So again you do the same thing, n goes here, e comes here, you do the square. So and this is the equation you get. Okay, so if somebody is looking for 95% of the data, he should have these many samples. If somebody is looking for 99.7% of data, then he should have these many samples. Now here there are two unknowns, s and e. So somehow you need to find the values of s and e to find out how many samples you should collect. Okay, one thing from here, this range, mean plus minus 1.96 e, or the ranges which are given by central limit theorem, the ranges which are given by central limit theorem for a specific limit of the data, for a specific range of the data, we call them confidence interval. Okay, so confidence interval is the range of the data which you get through central limit theorem using the mean and the standard error. Okay, so now we know that if I'm looking for 95% confidence interval, yeah, if I'm looking for 95% confidence interval, then I have to use 1.96e. If I'm looking for 99% confidence interval, then I have to change 1.96 to 3. Okay, so this percentage is what we call as confidence level. So the range is called as confidence interval and the percentage is called as confidence level. Okay, so I will say this range has a confidence level of 95%. The range which you calculated for our data using 1.96e, this range gives me, or this range is for the confidence level of 95%. Okay, and the same thing would be said here as well for the n values. If you are using this equation, then this n value is for the 95% confidence interval because you are using 1.96e, and this is for 99.7% confidence level. Okay, so the values themselves, the range of values themselves is called as confidence interval, and the percentage which the range is covering is called as confidence level. Okay, so these are some technical terms which you should know. Okay, so moving on to this thing now, we have to find out how many speeds must be collected. So how many samples, how many speeds, how many samples of speed must be collected to find out the true mean speed of the underlying distribution within plus minus 1 mile per hour. Okay, so this is my acceptable error. Okay, acceptable error is always given in terms of plus minus. Why? Because of the theorem. You see, a theorem has plus minus, right? The theorem has plus minus in it. Okay, so error is represented with plus minus. So this is my plus minus, and how much is my confidence level? 95%. Okay, and how this confidence level will change if you change, how the samples will change, how the number of samples will change if you change the error to plus minus 0.5 and if you change the confidence level to 99.7%. Okay, so they are asking us to use both these equations, this for 95%, this for 99.7%. Okay, so let me see how can I show it to you. Let's see. Okay, I'll go to Excel, much easier. Okay, can you see the Excel sheet, or did I just destroy everything? Okay, I believe now you can see the Excel sheet. Okay, so I'll put the confidence interval here, 95%, 99.7%. Okay, the error plus minus 1. Okay, but you have just imagine it's plus minus 1. Okay, and this one plus minus 0.5. Okay, I have to use these equations. So what is missing here? Tell me. There's something which is not given. What is that? E is not given. S is not given. Yes. Okay, S is not given because in the equation we are using S directly, right? We are not using E. We divided the E into S upon root of N. Okay, so we no longer need E, we need S. Okay, so S is not given. Okay, when S is not given, we will assume it to be 5 miles per hour. According to the book, S value of 5 miles per hour is a reasonable assumption. Okay, so I will assume S to be 5 miles per hour. Okay, so the first value will be S will be 5 and E will be 1, and you will get the value. Okay, so how much is the first value? If S is 5 and E is 1, how much you get? 96. Okay, so this was 96. Now you change E to 0.5. Change E to 0.5. How much you get? In the same equation, now you change E to 0.5. 384. Okay. Now you keep E as 0.5, but you change from 3.84 to 9. How much you get? 900. Okay. 900 is here. Now you keep 9 and then you change the E to 1. When you change E to 1, how much you get? 225. Okay. Okay. So these are coming from this equation, the second one, and the first column was from this equation. S was assumed and E was changing from 1 to 0.5. Okay. Now something which is related to your term projects. Okay, if I have to do the same thing for your term projects, what will I do? Now to get the S value to standard deviation, you must have a sample, right? You must have a sample. What we do normally is or what you have to do in your term project, let me clear that one first. In your term project, you have already collected 10 samples. Now, by the way, let me make it clear. Don't do anything in your term project. This is just an academic discussion right now. Okay, I'm telling you how things are done. Right now, it's very dangerous. I don't want you to go in the field. Okay, if it things don't get better, I may, you know, change the term project. Okay, so I don't want to be responsible for you going out and getting into any danger. Okay, so right now consider it like I'm explaining how things are done. Okay, like consider it theoretical. It's a academic discussion. Okay, so there are couple of ways how we can avoid assuming the standard deviation, or how we can check if my assumption is correct or not. Okay, so if you don't want to assume anything, what you can do is you take a small sample like you have done in your term projects, and from that sample you calculate the standard deviation. Okay, so you calculate the standard deviation from the small sample. So I maybe that in the end I find out that I have to collect, like in this case you found that you may have to collect 900 samples. Okay, so before you reach to that conclusion that I have to collect 900 samples, you can do a small 10-15 sample uh, trial, and you can calculate the standard deviation from there, and you can use it in this calculation. Okay, so in this way uh, I avoid assuming anything. Now I will not assume anything. Okay, because I have real data and I have calculated a standard deviation from that real data. Yes, but the data is small. Okay, the data is small. So using that, I will go back to the field and now collect the real sample. Okay, so if things get better and I tell you, okay, now you can go ahead and do it, then you should do it in this way. From the small data you have in the first submission, calculate the standard deviation, calculate the number of samples, and then you do it. Okay, in case you don't have even the small data as well. Okay, I'm doing it in another city, I cannot even collect a small set of data to get the standard deviation. What should I do in that case? Then you can do trial and error. Trial and error means what? You now calculated number of samples using a standard deviation of 5. Okay, so you assumed that standard deviation is 5, and let's say I'm going with these values. They look reasonable, right? Not too high, not too low. So I decided I will keep my error as 1 and my confidence level as 99.7%. So using the assumed value, I calculated that I need 225 samples. Okay. So now I will go and collect 225 samples. Okay. Now you have real data. So now you can calculate real standard deviation, not assumed, real standard deviation. So for example, you calculate real standard deviation, it comes out to be 4.8. Okay. So now you recalculate this value using 4.8. Okay. So instead of in the equation where you put 5, now you will put the real standard deviation. Okay. So when you calculate the real number with the real standard deviation, maybe the real number is less than 225. So actual sample needed was less, you got more. Okay, no problem. Let's say the real number which was required was more than 225. Okay, so let's say it was 230 now. So I needed actually 230 samples. I have 225. So what can I do? I can collect 5 extra values now. Okay, so then you can collect the difference. And in most of the cases, you may not have to do that because you may have more than what you require. 5 miles per hour is a very wide standard deviation. It's a very big standard deviation. So normally the numbers which we get out of 5 are more than required. Okay, so if you are using that, then it's a safe assumption because in most of the cases you do not need extra samples. In most of the cases you will already have extra samples. So this is how things can be done. This is how we can work out with the non-availability, unavailability of standard deviation. Okay. Now I'll move on to the next thing, which is before and after studies. I mentioned this thing earlier as follow-up studies or observational studies in the last slides. The slides of the last chapter or the last slides which we covered, data collection analysis. I mentioned it as before and after, we are saying it now, but I mentioned it as observational study or follow-up study. Anybody remembers what does it mean? Yes, what is the meaning of observational studies or follow-up studies? Anyone? What is this? We discussed different types of studies in the last lecture, like the slides earlier, and there one type of study was called as observational study or follow-up study. What did it mean? Okay, yes, when you make some changes and then you follow up for it, you track what what your changes are actually doing with the drivers and the highway. Okay, so this how we can track. We do a study before, we do a study after. So before and after studies. Okay, so follow-up study means the same thing, observational study means the same thing. Okay, you have data before, then a change on the road, and then a data after. This is called before and after study or a follow-up study. Uh, so in these studies, we are trying to answer two questions. We are trying to answer two questions. First question is, did our change on the road had an effect on the drivers in terms of speed? Remember, we are talking about spot speed. So we are talking about follow-up studies which are for speed only. So the first question is, did our change on the road had a significant effect on the driver's behavior? Okay. Now, to make sure, we have two data sets, right? One data collected before, one data collected after. These are the conditions we have to meet to apply the equations which I am going to discuss. The first condition is that both of them should be following normal distribution. Both of them should be following normal distribution, both data sets, before and after. If you collected enough samples, that you don't have to worry about it. So how many are enough samples? 30 at least. Okay. Now, in the example which we did, we got 96 samples, 384, 225, 900. Okay. All of them are more than 30. So when the calculated number is more than 30, you will go for the number, not for this 30 limit. Okay. And vice versa. If I calculated a number and it came out to be 15, then according to this rule, I will discard 15, I will take 30. Okay, so 30 is like the minimum limit. So wherever you are going below minimum, you will take 30. When you are going above minimum, then you will go for whatever is coming out. Okay, so before and after data should meet these conditions, not together, separately. Each data should have more than 30 samples, before and after both. Okay, so the two questions which we are trying to ask, the first question I already mentioned, did the change had a significant effect on the drivers or not? Okay, so if it had a significant effect on the drivers, that means their speeds will change significantly. The mean speed before and the mean speed after will be very different from each other. And the second question is, did we achieve the required change? Did we achieve the required change? I have a very good example to explain that. The one which you will like is somebody, let's say, repeats the course. Okay, so they have GPA 1.9 something, they got D in the course. Okay, so they want to improve it. Okay, they want to improve, obviously they want to get more than D, right? So if they get D again, nothing changes, right? So this answers the first question. If they get D again, this answers the first question. Okay, was there a significant change in the grade? The answer is no. But if they went from D to C, yes, there's a significant change. The grade has completely changed. Okay, so then the answer will be yes. Okay, now let's say they got from D to C. Okay, so yes, the first question is answered yes. Did we achieve a significant change? Yes. Repeating the course has significant effect on the grade. Yes. But this person has another problem. His overall GPA is 1.96 or 1.9 something, and he wants to get it over 2 to fulfill the requirement. To get it over 2, he doesn't need C, he needs A. So he has to go from D to A. Okay, so if he goes from D to C, the first question is yes, a change. If he goes from D to B, again yes, significant change. But in both these cases, if you go to the second question, your answer will be no. Did he achieve the required change? He wanted to go from D to A. So he got somewhere, but he did not go up to the point where he wanted to or she wanted to. Okay. So the same thing happens with the speeds as well. Okay. We will see some examples later on with the speed data. So how do I make sure about this? We will perform some statistical tests. Why are we doing these tests? Why don't we just look at the two values and say, okay, we achieve significant change and we achieve the required value or not? The answer is in the data distribution. You have two data sets. Okay. One is, uh, or let me get back to the example. Okay, let me go through it quickly, and through the example I will explain it. It will be much easier. Okay, so to answer the first question, did we have a significant difference in the mean before and after? We will perform a z test. Okay, and z is, if you remember, standard normal distribution. Okay, with the mean of 0 and the variance of 1. So first thing is, we convert our difference of mean to a z value, equivalent z value. To do that, x1 bar, x2 bar, x1 bar mean of the data before, x2 bar mean of the data after. Then we have sy. What is sy? This value. Okay, to calculate this value, I'm doing s1 square, meaning a standard deviation of the data before, upon n1, number of values in the data before, s2 square, standard deviation, data after, n2, number of values, data after. So we do this. Okay, we get the value of sy and put it over here. Okay, we put the means and we get z value. Now what should I do with the z value? If you remember, I told you last time, for a standard normal distribution, when I get the z value, I have a table, or I have softwares which can give me the cumulative probability directly. I don't need to calculate anything. Okay, so I have a z value, I have a z table. So this is what we call as a z table. Okay, and let's say you calculate the z value, and this z value was, let's say, 1.21. Okay, so how do we read this table? Your value is 1.21. So 1.2, the first two digits come from the first column. The first two digits from the first column. So 1.2 here. The third digit, last third digit, comes from the first row. So it was 1.21. So 1.2 here, first column. Then the last is 0.01, right? 1.21. So last is 0.01. So it will come from here. Okay. So I go 1.2 from here, 0.01 from here, and I get a cumulative frequency, cumulative probability of 0.8869. Okay, this table gives you cumulative probability for any z value. Okay, the z value is divided into first column and first row. First column, first two digits, first row, the last digit. Okay, in this case I get a probability of 0.88 something. Okay, what is the rule? So after I get the probability, I apply a rule. What is the rule? It's given here. If the probability from the table is 0.95 or more, the probability which you got from the table is 0.95 or more, then we consider the difference to be significant. So the before and after data are significantly different from each other. Okay, if the probability is less, then the change is not significant. Whatever you did on the road, it did not cause a big change in the speed. They are almost the same. Okay, so and the reason is, again, we are using the central limit theorem, 95% probability. Okay, so if it is more than 95%, that means that the z value has 95% chance of being higher than this, and there is only 5% chance that it is lower. Okay, so 5% is a very negligible value. Okay, so we say that yes, I can say with 95% confidence that there is a change in the speeds. Okay, so this is how you find out if the change is significant or not. Anybody has any questions? I will move to the example now. It will become clearer. But do you want to have any question right now? Okay. Moving on to the example. Okay. So before and after data is given, mean is given, standard deviation is given, number of samples are given. Okay. So they want to see if they impose a new speed limit on the road, and they want to see if the new speed limit uh, achieved the required change or not. What is the change they are looking for? 60. They are looking for a value of 60. Now, if anybody looks at the data, this is 65.3. This is 63 without any calculation. Without any calculation. If I ask someone, is this change significant? Is this change significant? 65 and 63. Is this a significant change? What will be your answer? Tell me. The before is 65, the after is 63. Is this a significant change in the values? No? Yes, somebody says yes as well. Equal, yes and no. Very good. Okay, so now you can see I can have a difference of opinion. Okay, I can have a difference of opinion. Some engineers may say yes, there's a difference, there's a change, and some may say there's no change. So this is why we are doing the Z test. So we are not leaving it to the opinion of anybody. Somebody may see this 2 miles per hour change as significant. Somebody else may see it as not significant. Okay, so this is where we are not leaving it to the judgment. We are using statistics to answer the question, not a person to think and come up from his own or her own mind that the change is real or not. Okay, so that's why we are doing it. Okay, so the first thing we have to do is we calculate the Z value. For the Z value, we need to calculate the SY. Okay, so I need the standard deviation and number of samples before and after. Okay, this is what we have. Let me, so SY equals to square root the standard deviation before 5 square divided by number of samples before, which is 50. Then standard deviation after 6 square divided by number of samples after 60. So what is my SY? Okay, then my Z value will be the difference of the means, 65.3 and 63. This whole divided by SY. So how much is this? 2.19. Okay, so if I go to this table, the Z table, I have three digits, right? 2.19. So the first two digits 2.1 from the first column, 2.1 is here. Okay, third digit 0.09 from here. Okay, so if I go from here and here, I get this number 0.9857. 0.9857. Okay, now the rule is yes. Okay, so according to the rule, is this change significant or not? Now tell me. So we have to apply the rule, right? So when we apply the rule, does this mean the change is significant or not? No, just done. We will calculate E later on, but we have to take the decision now. The change is significant because the value from the table became more than 0.95, right? Even if it was 0.95, we'll consider it to be significant. Okay. Now we will answer the second question. The second question was, did we achieve 60 miles per hour? Okay, but somebody looks at the data again, 60, 63. Again, the real question is it very close? I can say, oh yeah, we almost achieve it, or should I say no, we did not achieve it. So there can be a difference of opinion. So we will not say it now. Again, we will use now what Bayan was saying, the confidence interval. So we have to calculate the E now. Okay. In these examples, normally we use 95%, as you have seen in the Z table as well. We are following the 95% confidence level. Okay. So first of all, I will calculate the E value now. Okay. So E value is standard deviation upon root of n. So 6 upon square root of 60. Okay, so this is my E value. Okay, 0.77. Now we'll calculate 95% confidence interval. Okay, which was mean. The mean is 63 plus minus 1.96 into 0.77. Okay, it's the same thing which we use with the theorem here, same thing. Okay, but here in these tests we don't go for 99.7%, we go for 95%. Okay, so this is the range. Okay, so even if I take 95% of the center of the data, I'm still not getting 60 in the range. Okay, I'm still not getting 60 in the range. So now after calculating the range, I can say that I did not achieve the required speed of 60. I'm not saying it because the mean is not 60. I'm saying it when I calculated the range, 95% range of the entire data, it still did not give me 60. Okay, so I'm not basing my decision on a sample, I'm basing my decision on the 95% of the whole population. Okay, now a word of caution here. First we check the first question. Okay, we are answering two questions. So first question was, is the mean, if the difference in mean is significant or not? The answer was yes. Then we move to the second question. If the answer to the first question is no, there is no change in the mean, then the second question is automatically no. Going back to the example of the grade, if somebody had D and still has D, so there is no change in the GPA, right? The answer to the second question, did he achieve the GPA, change in GPA? No. Same thing here. If you did not achieve any change in the speed, that basically means you cannot go for the required value. Required value is after the change. Okay, the required value will come after the change. So we only go for the confidence interval check if we have already made sure the Z value was significant. Okay, that Z value was significant. Okay, another pithole where students make mistake. The table gives us the probability and the rule is on the probability, not the Z value. Remember my Z value was 2.19. Okay, but I need to put this Z value into the table and get the probability and then apply the rule of 90.95. Okay, so 0.95 is not for the Z value, 0.95 is for the probability which you will get from the Z value. Okay, I'll stop here. Yeah, what do we have next, right? Yeah, okay, so there's something new. I'll stop here. Do you guys have any questions? Are there any questions? If you don't have any questions, please do the scanning. Afikum. Okay, so I believe everybody is done. All of you have done it, right? Okay, thank you so much. See you next time, inshallah. Assalam.